We're now going to look at vectors. We've been talking about translation of graphs. Okay? So questions like this. Parabola y equals x squared, translated 2 units to the right, and then 1 unit up. What's the new equation? And so we say, oh, okay, start with our basic parabola. We'll shift it right 2 units, then up 1 unit, and we come up with a new one. X squared becomes x minus 2 squared when we move it across, and then it becomes x minus 2 squared plus 1 when we shift it up. So the new equation, y equals x minus 2 all squared plus 1, whatever that expands out to be. The beauty of vectors, well, why do it that way? I mean, so many things we shift both horizontally and vertically. Why don't we just do it diagonally? And so this is what a vector can do. So that new equation was done via a horizontal and a vertical. But I can combine them into one, what we call displacement vector. So I could have moved the origin straight to that point 2, 1 via one vector. That's what we call a displacement vector. Now, every single point can be moved using that same displacement vector. So I could pick another point over there and there and there, bang, and all of them will create the new parabola. So I just apply that vector to every single point on the parabola and I get this new parabola straight away. So I don't get confused with which one's which, I'm calling the new one capital X and capital Y. So basically what I've done, I've got the original coordinates. Now I've written them in what's called a column vector. So the original coordinates x, y, and we're basically adding the coordinates 2, 1 to everything. And we just do it like it logically is and simply add. And so using parametrics, so now instead of calling it little x and little y, I'm creating a parametric equation for the parabola. To make things simple, I'm just saying x is going to equal t, so y will equal t squared. So I get xy will now be t plus 2 and then t squared plus 1. So there's our new parabola in parametric form. So capital X will be little t plus 2, make t the subject, substitute it into the other one, and there's my new equation. So you can see we get exactly the same thing. That's the idea behind vectors. So some definitions. That was what we call a displacement vector. We name it PQ. You'll notice I'm moving from P to Q. So I'm going in that direction towards Q. So when I write PQ down, the arrow is going towards Q. That's our displacement vector that joins any point P to any point Q anywhere on the curve. P is what we call the tail of the vector. Q is the head of the vector. Some other notations for vectors. The first one, which is really hard to do when you're handwriting, is to put the letter in bold. But you might see that in textbooks or in tests and things like that. You might just bold the letter. But as I say, when you're writing your solutions, it's very hard to do that. How do you make a letter bold? So we don't tend to use it that much when we're writing out our solutions. But the other one that's very common is we put a tilde underneath the letter. So P with a tilde underneath says, oh, this is the vector P. Rather than calling it PQ, I'll just call it P. Now, every single vector is uniquely defined by its length and the angle it makes with the horizontal direction. So just like in trig, you remember we said the angle was always measured to the positive side of the x-axis when we were trying to work out the angles and bearings and things like that. So we do the same with vectors. It's always towards the positive x-axis, if you like, the positive horizontal. We use absolute value symbols to represent magnitude, because that's what absolute value is. Absolute value is the length and or the size of something. So we could say the absolute value, or the magnitude more correctly when we're talking about vectors, the magnitude of P tilde, which would be the same as the magnitude of PQ. They are the same thing, just written different ways. The size of the vector. Opposite vectors are simply directors in opposite directions. So if PQ, the vector PQ, we're labelling P, then the vector QP would be negative P. It's going in the opposite direction. Parallel vectors will have the same slope. I mean, that's what parallel is. So the vector PQ would be parallel to the vector QP. They'd be parallel, it's just one's going in one direction and one's going in the other direction. Then there's this really weird vector which is not a line at all, it's just a single point. It's called the zero vector. So it's going from P to P, so it's not going anywhere. So its length is 0, it's got no magnitude. But it also means it has no direction either, because it hasn't gone anywhere yet. And so what we weirdly say is it would be parallel to every vector, even though it's got no direction itself. A scalar is just magnitude without direction. So it's a number. It's just simply a number. So I am calling lambda there a scalar. So if I multiply a vector by a scalar, it's the same vector, but its length has been increased or decreased depending on what lambda is. So it'd be in the same direction as p, but would have a length of lambda times whatever the magnitude of p was. And then a position vector as opposed to a displacement vector. See, a displacement vector could be anywhere. We just go and find it. But the position vector is when the tail is at the origin. And then we call it a position vector rather than a displacement vector. Alright, how do we play with them? Because whilst they're lines, we do still think of them like numbers, and so we need to know how to add them and subtract them and things like that. Now, how do we add and subtract vectors? And visually what we do is we place them head to tail. You get the head of one and put it on the tail of the other, and then that will add them together. I've got the vector A, and I'm going to add the vector B. So I'll get A, and then onto that I'll add the B. Bang, that green one would be the vector A plus B. Where did we end up? So we started at the tail of the A, we finished at the head of B. So that would be A plus B. We talked about commuting. Well, these do commute because the order does not matter. Right? So if I went, I've got the vector B and I added the vector A, so this time I'm starting with B, adding the A, we get the same vector. Okay, I might call it B plus A instead of A plus B, but it's the same vector. Another way of expressing that. So PQ, the vector PQ, there it is, PQ, plus the vector QR would be the vector PR. Now when you've got it written in this one, it's sort of like you've smashed them together and the two Q's have gone, hey, you're the same as me, disappear. So I end up with PR. Now if I want to subtract rather than add, well I still add, but I add the negative vector because we know plus minus gives us a minus. So there's vector A. If I want to subtract vector B, then I would go, well there's A, but now I'm going to add negative B. Same vector, but in the opposite direction. I place it head to tail, and that would be A minus B. You're going in that direction there. The interesting thing is you can create a parallelogram with these two vectors A and B. The diagonals will end up being those two vectors. One of the diagonals will be A plus B, one of the diagonals would be A minus B. Let's draw it here. There was when I did A plus B, and that's what I got when I did B plus A. So the diagonal there is A plus B. But the other diagonal is A minus B. Or it could be B minus A as well, just depends on the direction. If the arrow was going the other way, it would be the vector B minus A, the negative of this vector. So that's addition and subtraction. What about multiplication? Well, to start off with, we're just going to talk about multiplication by scalars, so just by numbers. So that's very simple. All it's doing is enlarging the size of that vector by a factor of whatever lambda is. There's vector A, that would be vector 2A. They're in the same direction, but it's twice the length of the other one. That would be negative a half A. It's parallel to A, it's negative, so it's going in the opposite direction, and it's half its length. So it would be minus a half A. But all of them are parallel. They're all going in the same or the opposite direction, so they're all parallel. Okay, let's look at this little example then. We've got a triangle drawn up, but the sides of the triangle now I'm thinking of as vectors. So AB is the vector A, AC is the vector C, P and Q are midpoints, and R is a point on BC such that RC is twice the length of BR. Okay. We're going to rewrite the vectors BC and PQ, but just using vector A and vector C. How can we do that? I want to create the vector BC, and how I'm going to do it is I'm going to say, well, that would be AC minus AB. I haven't got the full parallelogram drawn up here, but if I did, this is the diagonal of that parallelogram, so it'll be one minus the other, and the direction tells me which one. So AC minus AB. Essentially, always think of a vector as head minus tail. So if you're wondering which one goes first in that, head minus tail. The head is C, the tail is B. They're both coming from the point A. So it's AC minus AB, head minus tail. And so that would be C minus A. PQ. Well, PQ would be a half of AC minus a half of AB, because AP, remember P was the midpoint, so AP we could think of as a half of AB, and AQ, Q was the midpoint there too, so it would be a half of AC. Head minus tail, so a half AC minus half AB, we'll get a half of C minus A. What does that straight away tell me? Compare these two vectors, what can we tell? Its length is half of it, because it's been multiplied by the scalar a half, but it's a scalar times the vector itself. So it's just a multiple of the other vector. So PQ is a half of the vector BC. So what property does that now demonstrate? Well, what we now know is if we join the midpoints of two sides of a triangle, because that's what we've basically done, we join the midpoint of two sides of a triangle, then that line will be parallel to the third side. Okay, let's go back. Remember we said PQ is a half BC. They're in the same direction. They've got to be parallel. But the other thing we know is it's going to be half its length as well. So when you join two midpoints up in a triangle, you're going to get something that's parallel to the other side and half its length. Let's try and find BR and RC in terms of A and C. Well, BR would be a third of the vector BC. They told us that one was twice the other. So it's simply a third of C minus A. RC would be 2/3. That was the other part of the line. So it'll be 2/3 of BC, so it'll be 2/3 C minus A. So now we're going to find AR. And they've given us the answer. It should turn out to be a third 2A plus C. AR, how am I going to get AR? I can get AB and BR and smash them together. The B's will disappear. And we've worked out expressions for these things. AB, remember, was A. They told us that. We just worked out BR was a third of C minus A. Now it's just like algebra. So I got A plus a third C minus a third A. Okay, playing around with it, I get a third of 2A plus C. So 8A is our introduction into this wonderful world of vectors.